Hello, my name is Jobey, and I'm accompanied by my teammates Linda and Dayan. And today we will be discussing electroless nickel-boron plating of piston rings in the aerospace industry. So a bit of background into our project. In the aerospace industry, components undergo extreme conditions in which friction and wear are the main contributors to the degradation of components, such as the piston ring. The piston ring is responsible for sealing the combustion chamber, and it limits the gas loss from the engine. Thus, the wear behavior is imperative to the engine efficiency and in minimizing part failure. To improve the tribological behavior, the surface of a cast iron or steel piston ring may be treated with a coating such as chromium via physical vapor deposition. However, there are shortcomings to this process, and we suggest implementing a solution that involves electroless nickel plating, as will be discussed by Dayan.
Thanks, Jobey. So, as Jobey mentioned, to improve the tribological performance of the piston ring, chromium-based coatings are the most commonly used in the aerospace industry. However, environmental concerns arise since it is a regulated toxic substance by the U.S. Environmental Protection Agency. Also, throughout its working life, cracks appear in its structure, which make the material less durable, in addition to being a very expensive product. Thus, to solve this issue, we will introduce the electroless nickel plating due to its less complex setup to coat complex structures, and it is also a very cost-effective technique. We will dope this electroless nickel material with boron to increase its hardness. And it has been shown that the electroless nickel-boron material has a cauliflower-like microstructure, which you can see here, and this will result in better wear and friction resistance. In addition, the environmental impact is reduced, and it will lead to also an increased durability, as well as less disposal costs due to recycling of the bath. So, we will introduce this electroless plating process during the finishing of the piston ring. We will first manufacture the piston ring, which involves making the CAD design, obtaining the raw material, performing the CNC machining, and after these steps, we will introduce the electroless nickel-boron plating. Afterwards, we will do heat treatment of the part to improve its performance, followed by the waste treatment of the plating baths. And now we will talk about each of these stages with more details.
Thank you, Dayan. So the initial step in our design process is the manufacturing of the piston ring. A design is made using computer-aided modeling, and the free shape of the piston ring is made using 4-axis CNC machining. There are series of machining steps: roughing and facing, finishing, drilling, and planar milling. Though the CNC machining process limits the hardness of the raw material to cast iron and softer grade steels, it is more conducive to batch manufacturing in the plating process, which will be discussed by Linda.
Thanks, Jobey. So when we look at the surface of the component, we must perform the following 4 steps before we can actually plate. The first is to clean the surface mechanically by scrubbing. The next is to chemically degrease using acetone. After this, we need to rinse with distilled water, and then we need to chemically activate the surface with either HCl or a Woods or Watts bath to make sure that we can actually deposit our material onto the surface of the ring. So after this, we put the component into the bath, which is made of the following chemicals. We have nickel chloride as the source of nickel. We have sodium borohydride as the reducing agent. This is to help with the actual process of depositing the ions onto the surface. We have sodium hydroxide to make the bath alkaline. And we have ethylene diamine and thallium acetate as the complexing agent and the stabilizer to make sure that the process is effective. We place these components into the bath for 3 hours at 95 degrees Celsius, and we ensure that there is consistent mixing to make sure that all surfaces are reached with these chemicals. So next we have the finishing and treatment steps with Dayan.
Thanks, Linda. So now that we have the as-plated nickel-boron composite, studies has shown that it has a superior tribological performance. However, its corrosion resistance will be decreased. In addition, it has an amorphous structure, which can be made crystalline by doing heat treatment on the part at 450 degrees for 1 hour. As you can see here in the graph, the hardness will be increased to up to 900, which is slightly higher than the chromium-based coatings, which are about 820 in the Vickers range. As a result of this improvement, we will also decrease the wear rate and the friction coefficient, as you can see in the tables at the right, which will improve the durability of the coating. And now we will do the environmental impact and mitigation analysis.
Thank you, Dayan. To address our design criteria to minimize the environmental impact, we introduce a treatment of the spent plating bath to the manufacturing process to extend the bath life. As shown in the graph, over time, there's accumulation of byproduct species that significantly reduces the plating rate by 46%. This will result in the bath needing to be disposed of. However, disposal processes are costly, and the Environmental Protection Acts in Canada limit the amount of industrial wastewater produced by manufacturers. Therefore, to extend the bath life, we introduced a two-step treatment process. These processes will remove species such as calcium hydroxide, iron 2 sulfide, and orthophosphate. In step 1, we have selective chemical precipitation, in which precipitating agents such as calcium hydroxide and sodium fluoride eliminate these byproducts. In step 2, we use electrodialysis, where electric potential drives out non-metallic ionic species. In comparison to the conventional processes of chromium plating, it approximately consumes 3,000 liters of water and produces approximately 75 kilograms of hazardous waste. With this treatment, we could reduce waste by 33% and minimize disposal costs by 77%, as the bath can be recycled up to 12 times in the manufacturing process. And now Linda will discuss the cost analysis.
Thank you, Jobey. When we take a look at commercial Electroless nickel plating, we see that costs can range from $15 to $25 per mil cubic foot. When we look at commercial piston rings, they can sell for $20 to $400, depending on the application and the engine type. So in order to make sure that our process is economically feasible, we decided on two main strategies. The first is selectively plating only the surfaces with high contact with the piston. This includes the groove and the ring side. By looking at only these two surfaces and plating them with this composite, we are able to optimize the plating, reduce the material used, while making sure that the performance of the ring is maintained. The second option is to optimize the plating rate. If we look at this chart on the right, we can see that by adjusting the concentration of the sodium borohydride, or the reducing agent in the bath, we can actually increase the plating rate. So if we make sure that the concentration is 1,000 milligrams per liter, we can see that regardless of the time, we're able to increase the plating rate, which decreases the time required for manufacturing of this ring. If we move on to the next slide, we can see that by adding the plating bath and also the heat treatment to the standard ring manufacturing process, we're able to increase the hardness, increase the durability, and also reduce the environmental impact of this process as compared to the current chromium plating. In terms of next steps and how to improve, we'd like to look at controlling the grain size of the coating, potentially incorporating other particles such as PTFE to make a more dynamic composite design, and also to increase the cost effectiveness to make sure that this is a process that can be adopted in this industry. And you can see by incorporating these steps and incorporating Electroless Nickel-Boron plating, we are able to make more robust piston rings that can be produced for engines in aerospace applications.